First, I would like to thank Planet and Tony and Matty for having us here. It's an awesome workshop, so thank you very much for organizing this. And I would like to thank Miguel for switching with me as well. Uh, so this is quite a big title for my talk. This is the title of a paper, General Method for Constructing Local Hidden Variable Models for Entangled Quantum States. So this is a joint work with Danny Cavalcanti, Leo Guerini, and Paul Skripchik. I'll try to ease into these concepts because there are a lot of concepts in the title. So inevitably, I'll repeat some concepts that you've heard before from great talks yesterday and the day before. So first, to start, I would like to say that my talk has a lot to do with this paper, the paper by Werner. This paper is from a time when things were not well defined, so has at least two big definitions in them. The first one is this paper defines what an entangled state is. So it's probably well, it's probably cited a lot because of this, but the main result is that Werner shows that entanglement does not lead necessarily to non-locality. So he gave the first examples of states that are entangled, but do not violate any Bell inequality or local. He presented a local hidden variable model for these states. After this paper, it took quite a while for people to bring local hidden variable models for other entangled states. It's a very hard task. You really have to show that for any measurement that you perform in your state, it has a local model. It has a local hidden variable model. So before entering into these details, this specific detail about local entangled states, let me introduce first non-locality, actually locality, what I call a local hidden variable model. So the scenario is the scenario that we've been talking about here in this conference for quite a while. You are used to it already. So we have Alice and Bob. They have black boxes where these boxes accept inputs and they give outputs. So we interpret it as Alice performing a measurement on her system and obtaining an outcome. And these boxes are correlated, and usually they are correlated. And the information we have about it is in this joint probability distribution of getting outcomes A and B given inputs X and Y. And if the correlations of these boxes come from this a variable lambda that we call the local hidden variable, then we assume that the behavior of Alice's box only depends on this variable lambda, this variable that's shared between Alice and Bob, and then the correlations have to be of this form, and then we say that there's a local hidden variable model for these correlations. And on another case, we have a quantum state. So Alice and Bob are performing measurements on a quantum state. The joint probabilities, they come from Born's rule. So they are of this form, where rho is the state of the system, of the quantum system, and the pi ax is a measurement operator associated to outcome A of measurement X of Alice, and the same for Bob. So this measurement operator, it can be a projector, then the measurement, we'll call it a projective measurement, or it can be a more general measurement, it's a POVM. But if all the joint probabilities that come from a given quantum state are of this form, then we say that the state is local. It admits a local hidden variable model if this happens for all measurements that you perform on the system. So, well, I cited these two cases where the measurements can be projective or POVMs, and we can say that the state is local for projective measurements or local for POVMs. Being local for POVMs is stricter. So, I'm going to define states that such that all correlations are of this form as LHV states, just for short, because they admit local hidden variable models. This said, I'm gonna go for the paradigmatic system, the state, better saying, the Werner states of 2-qubit systems. These are by far the most well-studied states on this relation between entanglement and non-locality. So we know that these states that are parameterized by this, they're just a convex combination of the singlet and the maximally mixed state. They are separable for any value of W that's less or equal than 1/3. And then Werner, in his paper, he showed that these states, they admit local hidden variable models up to W 1/2 for projective measurements. And then Barrett, he showed that these states, they admit local hidden variable models for POVMs for values of W up to 5/12. Then Tony and collaborators, they show that this problem is actually related to another problem in mathematics, that's a problem related to this Grothendieck's constant. And then they show that these states, actually, they admit local hidden variable models for projective measurements up to a value that is close to 2/3. I guess not exactly 2/3, but it's close to 2/3. And then we know that these states, they violate the SHSH inequality for values of W that are greater or equal than this value, 1/√2. So since then, there have been some improvements on this. You see that on this, there's a gap in here that we don't know if these states, they admit local hidden variable models or if they violate some other Bell inequality. So in the last years, there have been some improvements in this. And the latest I'm aware of on these papers by Flavian Hirsch and collaborators this year, and this one really at all. In this paper, they managed to conclude that these Werner states, they're local for projective measurements for up to values of W of this. And in this other paper, they show that these states, they violate an inequality for values up to this. If you're curious about these numbers, you can ask Miguel. I think he's in both papers. So he probably knows more about this. There's this very nice result from the group in Geneva, where if you have a state rho that is LHV for projective measurements, then there's this other state rho prime, defined like this, that is LHV for POVMs. So proving that a state is LHV for projective measurements is already a hard task. And proving it is LHV for POVMs is even harder. You see in all these works I've shown here, most of them are for projective measurements. There's only one that's for POVMs, Barrett's. So this is a nice result because of this. Once you have a state that is LHV for projective measurements, then you know how to build a state that is LHV for POVMs. Well, actually, it may not be that good because you're mixing a lot your state with a lot of separable states here, so you may lose entanglement. So in the end, your state may not be entangled. But still, this is a very nice technique for you to obtain states that are local for POVMs. If you choose well your state rho here, and you know it's LHV for projective measurements, then you may end up with a state that is local for POVMs and is entangled. Okay, so in this paper, actually, they have an example of this. I state that. Yes. Uh, Now this is the local dimension. Yes, the dimension each part. Yeah. Yes, exactly. Rho A and rho B are the reduced states. Sigma A and sigma B are anything. Yes, exactly. They are arbitrary states. Okay. All right. So let me move to another scenario, steering scenario. Has a lot of similarities with the null locality scenario and some differences. Okay. So in the steering scenario, we have Alice. She has a black box, same thing, has inputs and outputs. But Bob has control over her systems. So we assume he can perform a tomography and he knows the state he has. Okay. So this scenario is characterized by these quantities here. These are the states of Bob that may be correlated with the outcome and measurement performed by Alice. So these things here are actually not really quantum states because they're not normalized. And the set of these unnormalized states, we call them assemblages. So this scenario is characterized by this. So we now can see correlations between the states that Bob observes and the measurements that Alice performed. Okay. In case, well, this scenario is motivated actually by a case where Alice and Bob, they share an entangled state, and then when Alice performs a measurement, she actually steers Bob's state. Okay, but it could be the case where the state in Bob's part doesn't come from an entangled state that's shared between Alice and Bob. It comes from, actually, there's a state in Bob that is correlated with the measurements in Alice, but this correlation comes from a lambda, a hidden variable, more or less in the same way as in the non-locality scenario. So if this is the case, then we say that the assemblage, well, yeah, if this is the case, the assemblage has to be written in this form, where the sigma lambdas are the states that Bob receives, and lambda is this variable that is correlating the results in Alice's side and the states that Bob receives. And if this is the case, the assemblage is unsteerable. We say that the assemblage has a local hidden state model. So these sigma lambdas are the local hidden states. Again, it could be the case where the correlations come from a shared state rho between Alice and Bob, and the assemblage comes from tracing out the state of Alice of rho when the measurement pi AX is applied on Alice system. So if the assemblage has a local hidden state model for all measurements that Alice performs for a given rho, then we say that this rho admits a local hidden state model. So this rho, I'm saying that the state has this property that it's always local, that it has a local hidden state model. Okay. The same way as I said before that the state has an LHV model. Now I'm defining that the state has an LHS model. If this is the case for all projective measurements or for all POVMs. One funny thing is that if a state admits a local hidden state model, then it necessarily admits a local hidden variable model. So you could see clearly here if the state admits this case, then a measurement performed, if Bob performs a measurement on his side of the state, then you can see easily here that the joint probability will be a local joint probability. So if a state admits a local hidden state model, it necessarily admits a local hidden variable model. But the converse is not necessarily true. So there may be states that have local hidden variable models, but they don't have local hidden state models. Okay, but anyway, there's this image of the sets of states. So we have like all states, then the separable states, a little bigger the set of LHS states, and then the set of LHV states, and the rest, the other states. So it's easier, in some sense, to study the LHS states than to go for LHV states. And I made this big introduction to say that that's what I'm going to do from now on. I'm going to study, I'm going to focus on states that are LHS, because I know that in the end they are LHV as well. But I'm not necessarily going to study states that are necessarily LHV. So let me talk about the method. As I said, so far, it's really, really hard to attack this problem, to get an entangled state and to prove that it has a local hidden variable or local hidden state model. Our method is a method that you can, is a general method where you can you can algorithmically test if a given state is local or not. So let me explain more or less how it works. First, assume that your state has an LHS model just for a finite set of measurements. It doesn't have to be all projective measurements. Say this is the Bloor sphere. Suppose we have qubits, and then the measurements you're considering are the measurements on these arrows. Okay, so these are only 3 complete measurements, so 6 arrows, and assume the state is local for these 3 measurements only. Okay, so let's say these pi here are only these points on the Bloor sphere. If this is the case, then it necessarily is the case that your state is local also for the convex combination of all these measurements. So if it's local for these vertices, it's local for the whole hexagon. In particular, the state is local for this ball over here, the biggest ball that fits inside the heptagon, the polytope that you obtain when you make the convex combination of these finite points. So I started from the assumption that the state is local for these 6 measurements. Now I know that it's local for all this ball here of radius r, and this ball here is an image of the whole set of measurements, but smaller. Okay, so now I know that my state is local for all these measurements that are the same as all projective measurements, but smaller. You know, so these new measurements, they're the measurements in the ball. They are convex combination. They are the measurements in the sphere, in the outer sphere, but depolarized. Okay. So I realized this. Now I know that my state is local, has an LHS model for all measurements that are the projective measurements, but depolarized. Okay, I'm applying the depolarizing channel on these measurements. So this is my assumption. I know that my measurements are the projective measurements, but depolarized. One cool thing is that I can, instead of depolarizing the measurements, depolarize the state. So I'm depolarizing the projective measurements on Alice's side. I can depolarize the state on Alice's side, locally depolarize on Alice's side, because the depolarizing channel itself dual. So there's this this particularity from in this specific case. So instead of depolarizing the measurement, I can depolarize the state, and it's the same thing. The level of the assemblage is the same thing. So I'm operating here on the left hand side, but the right hand side is just here to remind me that my state is local for the measurements I'm considering. In the end, I end up with another state, rho prime, that is rho depolarized, that is local for all projective measurements. So just let me go back a little bit. I started from the assumption that I have a state rho that is LHS for a finite set of measurements. Just following these 4 equations, I concluded that I have a state rho prime that is LHS for all projective measurements. All right? Where rho prime is just my state rho locally depolarized on Alice side. Okay? So this is the trick. If rho is LHS for a finite set of projective measurements, then rho prime, that is rho depolarized, is LHS for all projective measurements. So now I have an idea on how to show that states are LHS for all projective measurements, based only on a finite set of measurements. I can invert this logic and make a test out of it. So I'll say that rho is LHS for all projective measurements if, for a finite set of projective measurements S that I choose, there is an operator O that is LHS for S, for this finite set of measurements, such that rho is this operator O locally depolarized. Why am I claiming, why am I saying O instead of rho and rho prime? Because we realize that this operator O, it doesn't have to be a state. It doesn't have to be positive. Okay, it's just an operator that when you depolarize, it gives you rho. If this operator is LHS for some finite set of measurements, then you're done. Then you know that your state rho is LHS for all projective measurements. So this is a sufficient test, of course. I mean, you cannot claim that if your test fails, you cannot claim that your state is not LHS. But if the test doesn't fail, if the test succeeds, then you know for sure that rho is LHS for all projective measurements. So this is how the method works. We can formulate this method as an SDP. So this is why I said before that you can go on the computer and test for a given state. So given the state that you want to test for projective measurements, in this case, given the state you want to test, a finite set of measurements that you choose. This finite set of measurements will define a polytope on the Bloor sphere, and this polytope will have an inscribed in sphere that will have a radius r. So this radius r is important because it's the degree of depolarization that you're going to apply. Okay, so given these things, your test is to find an operator O and local hidden states, sigma lambda, such that your operator O is LHS for the finite set of measurements. So this equation here it says this. Well, I changed the notation. It's not an integral anymore. It's just a sum, because well, I have a finite number of measurements, and all I need, I don't need like all probability distributions here. I need only the deterministic probability distributions. Okay, but the number of deterministic distributions, it scales really bad with the number of measurements. Okay, so it scales exponentially with the number of measurements. So if you take a set S with a lot of measurements, then you're gonna end up with a lot of deterministic distributions, and then the test is not going to be practical. Okay, but continuing. So you want to impose as well that your hidden states are positives and definite for all lambdas, and of course that your rho is this operator rho O depolarized, locally depolarized on Alice. So this is a feasibility problem. Okay, you ask you program this, and the program will ask if there is an O and hidden state such that this holds. If there is, then you know that your state is LHS for all projective measurements. If there isn't, then you don't know. Then maybe you change the your finite set of measurements. Of course, if your set of measurements is the set of all projective measurements, then this becomes a brute force test. If you increase your set of measurements such that these becomes all projective measurements, then it's not practical. But what I'm saying is that if you increase this set, then somehow it will converge to this SDP will become necessary as well, not only sufficient. Okay. So if you want to go multipartite, this holds as well, but you want to impose that all your sigma lambdas are fully separable. This is not really practical, but in the case where you have only 3 qubits, then these sigma lambdas, they will be the states of like 2 bobs. So it's going to be a 2 qubit state, and then you impose PPT. This is an SDP, so it holds. This can also be generalized to higher dimensional systems. So I'm talking about Bloor spheres all the time. So I'm using qubit language, but you can create, you can consider projective measurements in higher dimensional systems as well as vectors in some higher dimensional spheres. Not all vectors will correspond to projective measurements, but certainly all projective measurements will have vectors correspond. So the whole argument holds. You can still choose a finite set of measurements. These finite set of measurements will define a polytope. You can consider the biggest sphere that sits inside this polytope, and the whole argument holds. Okay. The only difference is that not all vectors will be measurements, but you still can take the set of all projective measurements and depolarize it somehow. Okay. The problem is, in practice, this is not feasible, because once you go high dimensional, then you have to consider a lot of measurements. So your polytope will have a volume on this big sphere, and then when you take a lot of measurements, then memory explodes because of the number of deterministic strategies. Okay, so this is very general. The method in principle is very general. In practice, not so much, but in principle it is. That paper I cited before by Hirsch et al., where they say that if a state is LHV for projective measurements, then there is a state that is LHV for POVMs. It also holds in the case where only one party is, it also holds for the case of LHS for the steering scenario. And it's simpler, because now there was this state before where with a lot of terms. Now this state is much simpler, and the amount of noise that I wouldn't say noise, but you're mixing your state rho with a separable state, and now it's less noise that you're mixing it with. So your chance of losing the entanglement of your state is smaller now, because there was this problem, right? Because if rho is LHS for projective measurements and is entangled, well, it may not be so much entangled. So when you mix with a separable state, then you may lose entanglement, and that's not what you want. Of course, separable states are local, and there's no fun in it. So it only makes sense to consider states that are entangled and LHS. So these are the ones we're looking for. So now we can apply this result into our previous SDP. So this is the previous SDP. We're looking for operator O such that this holds. If this holds, then we can move back to this. And then a new state rho prime will be local, will be LHS for POVMs as well. So we can just plug it here. So given a rho, you want to see if it's local for POVMs, if it's LHS for POVMs, then this is the SDP you have to implement. You only have to change this last line. Okay. Yes. Yes, exactly. Yeah. What I'm doing is the same thing as before. I'm showing that I'm trying to show that the state is that some state is LHS for projective measurements, but then since I know that that state is LHS for projective measurements, then I know that rho prime is LHS for POVMs as well. So I'm doing pretty much the same thing. But the conclusion is a different one. Okay, so I reach another result. I know that the state is LHS for all POVMs, even though I'm not explicitly considering POVMs here. Okay. There's a caveat here that is this sigma A is the same as in the definition before, so it's arbitrary. You have to choose. So maybe I should have put here given sigma A as well. All right. So these are feasibility problems, right? Try to find O. I'm not minimizing or maximizing anything. I could minimize or maximize some linear function of these operators. And this is what we're going to do to construct states. Now we're looking for LHS states that are as entangled as possible. And how can I do this in this framework? I can consider entanglement witnesses. So we construct examples of entangled LHS states by considering this problem. Now I want to, given a witness, an entanglement witness, I want to minimize this value. Now rho is a function of this operator O here, given by this relation, okay? So I want to minimize this. If I succeed, if I obtain a negative value, then I know that my state is LHS and entangled. But I can iterate this process. I obtain a state. Then I can try to find the best witness for that state. That's an SDP as well. I didn't write it here, but that's an SDP. So look for the best witness for a given state. Now I come back here, I plug this new witness here, and then I run the program again, obtain a better state, a more entangled state. Then I iterate the process. With this, we managed to obtain a long list of new entangled states that are LHS, and they're as random as we could access. You know, they don't have like any particular symmetry. They don't. They're random in some sense. Okay. When we did this, we considered like 8 or 9 different witnesses, so we could maximize different aspects of entanglement. So we have a huge list of states, but just by doing this problem. So this is how we, in the end, construct entangled LHS states. So we have this method to test if a given state is LHS or not, and we have a method to construct entangled states that have LHS models. Let me give a few examples. So first test we performed, let's look at what we can do with Werner states. Werner states we know. Well, we know more or less everything about them. In the case of LHS, we know even more, because we know that they're LHS if and only if this W here is less or equal than 1/2. Okay. So with our method, we managed to certify that these states are LHS up to W 0.44 here. So we managed to certify 90% of LHS Werner states with a finite set of measurements. Which finite set of measurements? The measurements given by the vertices of this guy here, the rhombic-cube octahedron. Okay, it has like 24 vertices, so it's equivalent to 12 measurements. Okay, because well, a vertex and the antipodal vertex they are a measurement. Right? And the biggest sphere that fits inside this guy has a radius of 0.86. Remember that we want the biggest sphere possible, because this sphere, if this sphere is too small, then it means that you're depolarizing a lot your state. If you depolarize a lot, then you lose entanglement. So we want the biggest sphere inside the polytope with the minimum amount of vertices possible, because as soon as the number of vertices increase, the number of deterministic strategies increase as well, then the computer doesn't run anymore. So this is pretty much as high as we can get, 12 measurements. It's almost, yeah, I couldn't do more than this. Okay, so with 12 measurements, I already was able to certify that almost 90% of LHS, of Werner LHS states. Okay. And now we tried some examples on the tripartite case as well. So we considered isotropic W and GHZ states. So mixtures of W states and GHZ states with the identity. Okay, so we know that GHZ state, this noisy GHZ state is separable up to 0.2, and the W is separable up to 0.209. And then with our method, we managed to certify that these guys are LHS up to these values here. So we now know a range of these states where they are entangled and have LHS models. Okay. So yeah, as far as I know, we don't have as many examples of multi-part or tripartite or multi-partite states that are entangled and are LHS. Actually, with our method, we managed even to get states that are genuinely multi-partite entangled and still have LHS models. Okay. So to one of the last thing we did, and I think it's a very cool thing, is that with our method we could estimate the volume of states that are LHS. So we pick a state at random, we ask if it's entangled. If it is, then we can use our method to test if it's LHS. So now we can estimate how big the set of LHS states is compared to the set of separable states. That's what we did. So I showed this picture before, where I draw in any way these sets, but actually my intuition was that both sets of LHS and LHV states were very close to the separable states. Were like just as a thin shell outside the set of separable states, and well, we now can test this, how big they are in comparison to one another. So the method is just pick a state at random, but to pick a state at random, there are many ways of doing this. Okay, it depends on the measure you consider in the set of states. So I did it for Hilbert-Schmidt measure. I took 20,000 states at random from the Hilbert-Schmidt measure. 23% of them, more or less, were separable. And this agrees a lot with a result from Slater, where he says that 24.2%. This result is from geometrical arguments, okay? So it's really considering the geometry of the set. So I thought it was okay, you know, like I thought I was really picking up uniformly states from the Hilbert-Schmidt measure, okay? So from this, I consider only the entangled states, and a quarter of them were LHS. I was really impressed. Like, I thought this number would be like 1% or so, but 1/4 of the states, of entangled states I picked at random, were LHS. If I consider also the Bures measure, it predicts that I got 7% of them, of the states separable. The prediction is 7.3, so I think I was picking the states at random as well. And in this measure, I found that 7% of the entangled states are LHS. Well, not as much as here, but still a lot. Why is this important? Because if your thing is device-independent protocols, then you want non-locality. This is saying that there are plenty of entangled states that will not provide you non-locality. So these states are useless from the point of view of device-independent protocols, okay? And there are a lot of them. So to summarize, it's usually very hard to prove that a given state is LHV or LHS, okay? And now we have a method that provides a sufficient criterion to do so. it is general because it it can be, in principle, it can be applied to any state, but in practice, not so much. If you go to high dimensions or to multipartite, then the computer becomes too slow. You know, the time required and the memory required is too much. And this method can be adapted to construct new examples of entangled states that are LHV or LHS. And as I lastly said, it can be used to provide lower bounds. Why lower bounds? Because the method is sufficient. I may be missing states, of course. I may since the method is not necessary, all I know is that at least, yes, I should have said this. These numbers is at least 25% of entangled states are LHS. Okay, so this is a lower bound, maybe more. For this, I consider, I don't know, 10 measurements, not even the 12 from the solid I showed before. So yeah, that's it. These results I showed you was recently published in PRL, and this paper has a sibling. This one here, instead of a 1, is a 2. Okay, so check also this paper from the group in Geneva, from Nicolas Brunet group, has almost all the things I said here. It's also in this paper as well, with a different twist. So it may be cool to check out this paper as well, because they managed to get a very similar thing in the same time. Okay, so with this, I thank you.